We will start talking about solutions by introducing the very concepts or the very magnitudes that a solution is made out of. A solution is pretty much a homogeneous mixture. A homogeneous mixture, by definition, something we already talked about before, is when two or more compounds mix at the molecular level. That means the different components cannot be observed with the eye, not even a microscope. They are intimately mixed and they are homogeneously distributed. That is, that at any small amount of solution that you take, the proportion of the different components will be the same. We will call solute and solvent as those two components or more. Solvent will typically be the most abundant, and solutes will be the ones that are not solvent. Most of the times, the amount of solvent is so much more abundant than the solute that it'll be pretty evident to distinguish those two. In the case that they are not, when the solute and solvent are not discernible in quantity, we will say that the substances are miscible, which is just a very, typically will be a liquid-liquid solution when you can add any quantity of both, and that's still a solution, but you will not be able to distinguish between solute and solvent. What makes a solute and solvent mix? That will strongly and exclusively depend on the intermolecular interactions between the solute and the solvent. I said exclusively, but of course there will be other factors such as temperature, pressure, etc. The limit to which you can dissolve solute in a solvent, that's called solubility. So, as I said, some properties of the solutions is that a solution by definition is homogeneously distributed. That means that if you were to raise a wall between a solution and pure water, after a while, the amount of, in this case, sodium chloride would be homogeneously distributed throughout the now two containers. So that's a very important property. They are all homogeneously distributed. So what kind of solutions do we have? It depends on the solute phase and the solvent phase. So we can have a gas-gas, you can have a gas-liquid, liquid-liquid, solid-liquid, or solid-solid. In the case of solid-solid, you may imagine that being homogeneously distributed may not be as easy because some specific atoms of solute may be trapped in some areas of the solute. But in the other case, imagine the solute and solvent are homogeneously distributed. Okay, so let's see if we can understand what solute and solvent are in 4 everyday examples. In this case, the first picture, it's asking for identify the solute and the solvent and the phase of solute and the solvent and the kind of interactions. Well, in a fish tank, the reason why a fish can breathe is because you have oxygen. So you will have oxygen gas as your solute and water, liquid, as your solvent. Okay, and the kind of intermolecular forces that these two have, at least they have in common, they have in common is dispersion, because even though water can do hydrogen bond, oxygen cannot. Okay, now let's see ammonia. I'm going to this picture on the right, this one here. It's a cleaning product. Ammonia dissolved in water. How do you know it's dissolved in water? Because this bottle is made out of liquid, and ammonia boils at negative 33.3. So ammonia is a gas. Ammonia is a gas dissolved in water that is a liquid. Ammonia would be the solute and water would be the solvent. Now, what kind of interactions can make solute and solvent stick together? In this case, both of them can have hydrogen bond. Okay, so another example. You have a white vinegar bottle. Luckily for you, white vinegar, when you buy it at the store, it's diluted acetic acid. The word vinegar comes from the Latin bitter wine. That's what happens when you let wine go bitter. It becomes from ethanol to acetic acid, right? The functional group gets oxidized from alcohol to carboxylic acid. And because it boils at 118 at room temperature, acetic acid is a liquid, and of course, water is also a liquid. So in this case, the solute is a liquid, and the solvent is also a liquid. And what kind of interactions do they exhibit among solute and solvent? Again, this will be hydrogen bond. Okay. Finally, sweetened water. Of course, what you can see here, this may be tea. It contains a lot of things, but if it's sweet, I'm going to assume that it's either glucose or saccharose or any kind of sugar, carbohydrate. So just to make things simple, this is the formula of glucose. Probably it's not glucose, but something sweet. Glucose is sweet. And this one is solid. And this would be our solute. And water, again, liquid, is the solvent. If you remember the formula of glucose, I can draw it here. Oh, this could be, if you remember from your organic chemistry. There's a lot of possibility of hydrogen bonds, therefore the kind of interactions that solute and solvent can form is hydrogen bond. Why do I insist on the kind of interactions between solute and solvent? Well, because this will justify if a solute is soluble in the solvent. Again, the kind of intermolecular interactions between solute and solvent, this will justify, if they are strong enough, will justify the solubility, that is the capacity of the solute to dissolve in the solvent.